In this video, I hope to clarify some of the misunderstandings and confusing bits of understanding electrochemical cell structure, and to do that, we're going to work through a sample electrochemical cells problem step by step so that hopefully all concerns will be eliminated. So the first thing that we need to do is determine which reaction occurs at the anode and which half reaction occurs at the cathode. Now, you'll remember that it is the oxidation reaction that occurs at the anode, and the electrons that are lost in the oxidation reaction will flow through the connecting wire and be used to power the reduction reaction that occurs at the cathode. And if we remember that the purpose of an electrochemical cell, or indeed of any battery, is to generate electricity, we simply need to look for the combination of half reactions that produces the largest voltage. So as you can see, just like in our data table, our two half reactions here are both written in the reduction reaction form, and we can see that only one of these reduction reactions has a positive voltage, which means because reaction 1 has a positive voltage, this is going to be the reduction reaction in our electrochemical cell, and therefore this reaction is going to occur at the cathode. Conversely, because the zinc half reaction in the reduction form has a negative voltage, we can assume that if we flip the zinc reaction the other way and turn this into the oxidation reaction is going to have a positive voltage, and therefore this is the half reaction that occurs at the anode. So the oxidation reaction is a pretty typical one where we start with a metal in its metallic form, and usually, not always, but usually the same metal that undergoes an oxidation reaction makes up the material that we find in the solid part of the anode, which we remember is what we call the electrode. This is the part of the anode that actually conducts electricity, and in the case of this electrode, the solid part of the anode is made of the metal that undergoes the oxidation reaction. But as we'll see in the cathode, this is not always going to be true. Now, when zinc is oxidized, it is going to lose 2 electrons, which then flow away from the electrode in the anode through the connecting wire and eventually are going to end up at the cathode. Now, when zinc metal is oxidized, it forms the Zn2 plus ion, which is dissolved within solution, which again is why we write it in the aqueous phase of our anode, which again is what we call our electrolyte, because it's an electrically conductive solution that contains ions. Now, we'll look at the flow of ions within electrolytes once we finish understanding how each of the half reactions occur at each of the anode and cathode. So let's go to the cathode reaction here. Now, the 2 electrons that every zinc atom gives up are eventually going to end up in the electrolyte of the cathode, and we can see this from the cathode reaction because we can see that the starting form of our compound that undergoes reduction is actually not a solid metal. It's actually the permanganate ion, which we can write in solution because we can see that this ion exists in its aqueous form. Now, if there's any doubt that this ion here undergoes the reduction reaction, we can prove that by calculating the oxidation numbers of the metal manganese. So if we do it with manganese 4 oxide in the products, we know that oxygen has an oxidation number of 2. Negative 2 times 2 is negative 4. And to balance out this charge, manganese is going to have an oxidation number of positive 4. Now, if we compare this to the oxidation number of manganese in the permanganate ion, again, start with oxygen's oxidation number, negative 2. Negative 2 times 4 is negative 8, and negative 8 plus X is equal to negative 1. So X, our oxidation number of manganese, would be positive 7. So we can see, because of the decrease in oxidation number, that the permanganate ion is going to gain the electrons from the anode reaction, and when it undergoes the reduction reaction, it is converted into the solid form, which is manganese 4 oxide. And because this is the solid form, this is the material that actually precipitates out of solution onto the solid electrode within the cathode. So here we can see that our starting compound actually begins in solution and finishes as a solid part of the electrode, which is the opposite of what we saw here. So in terms of identifying which form of the anode or cathode reaction starts in the electrolyte and which starts or ends up on the electrode, all that you need to do is simply look at the state of matter to understand which goes where. And this is the general format of how the electrochemical cell actually generates power, but we have a problem if we look at each of our electrolytes. So we can see this more obviously in the anode's electrolyte. As the oxidation reaction occurs, the concentration of Zn2 plus ions is constantly going to increase, meaning that the positive charge is also going to constantly increase. Now, remember that positive charge cannot exist by itself. It needs negative charge in order to balance itself out, because charge by itself is unstable and will naturally want to migrate to the opposite charge. So we need an anion in our anode electrolyte in order to balance out the charge of zinc. Usually a popular choice for this is nitrate, because it's relatively common, and we remember from the solubility rules that all nitrate salts are fully soluble as long as we have enough water, which means even though we have negative charge to balance out the positive charge of zinc, zinc and nitrate will not form a solid precipitate and don't have any risks about interfering with this electrolyte. Now, the second problem with the fact that zinc accumulates is that eventually the positive charge of the zinc is going to overwhelm the nitrate that we have in this solution here, and eventually we're going to have too much positive charge. Now, why is this extra positive charge important, or why is it a problem? Because again, all positive charge is naturally going to attract to negative charge, which includes the electrons that are released from the anode reaction itself. Now, if these electrons are attracted to the extra positive charge here that is building up, that means they're not going to flow through the connecting wire, and we're not going to get any current at all, which is why in every battery, and especially in electrochemical cells, we have this part, which is what we call the salt bridge, that allows the extra positive charge in the form of these Zn2 plus ions to migrate away from the anode towards the cathode, so that the positive charge doesn't build up within the anode and the electrons can keep flowing from anode to cathode like so. Now, if we analyze the reduction reaction at the cathode, we will find the opposite problem is there, although it's a little bit hard to see, because as the reduction reaction happens, the concentration of the permanganate ion is going to be falling as it is consumed, which means you would expect that the amount of negative charge in the cathode is also going to decrease, but that's not looking at the overall reaction. Because if we also consider the fact that this is balanced in acidic solution, as the permanganate is consumed in the reduction reaction, we can see in our reactants that acid is also consumed by this reaction, meaning that we have a positive charge that is constantly decreasing as our reduction reaction happens. Now again, we have the same issue in our cathode's electrolyte as our anode, where we need a negative charge in order to balance out this positive charge, especially since permanganate is being consumed. So again, nitrate is a popular choice because again, all nitrates are fully soluble in water, and we remember that HNO3, nitric acid, is a strong acid, which means that it is going to ionize 100% of the way, meaning that H plus and NO3 minus will not reattach to each other, and the nitrate exists simply to balance out the positive charge. However, we see that as hydrogen is consumed by our reduction reaction, the nitrate is not going to react at all, meaning that we are going to have more negative charge than positive charge as our H plus is consumed, meaning that the negative charge is going to get stronger. Now again, this is a problem for the generation of electrical current because the electrons that are flowing from the anode to the cathode do not want to be near this negative charge that's accumulating, which means that the repulsion is going to disrupt this current and we're not going to get any power. Unless, again, we use the salt bridge and the extra NO3 that is building up in the cathode can use the salt bridge to migrate towards the positive charge found in the anode and therefore counteracting the buildup of negative charge in the cathode. So that concludes our summary of the structure of the electrochemical cell and the movement of ions and the movement of electrons that takes place in between each half. The only thing that we have left is to write the overall reaction and determine the overall voltage based on our starting half reactions. So just like within any redox balancing situation, we need to take a look at the total number of electrons in each half reaction, and we need to find the lowest common multiple in order to find out how to make these electrons equal. In this case, the lowest common multiple between 2 and 3 is 6. So we're going to take reaction 1 and multiply it by 2, and reaction 2 and multiply it by 3. And if we write each of those down here, we would have 3 zinc metal atoms plus 2 permanganate polyatomic ions plus we have 2 times 4 is 8H plus in the reactants, and then I'm not going to bother writing out our electrons because they of course cancel, and then if we write out our products, we have again 3 Zn2 plus ions, and then if we take the products from our reduction reaction, we have 2 manganese 4 oxide and 4 water molecules, and you'll find if you count up the total charge on both sides, you find that it should balance. We see 3 times positive 2 is positive 6, positive 8 minus 2 is positive 6, so the charge is balanced without the need to write in electrons, and you'll find the same for all of the atoms within the reactants and products of our combined reaction. And of course, we need to remember that because each of the voltages are listed in the units volts per electron, it doesn't actually matter what we multiply our half reactions by. The voltages are going to be constant and not affected by the lowest common multiple multipliers. So all we need to do is take the voltage of our oxidation reaction and add it to the voltage of our reduction reaction, and we can calculate the total volts per electron of the electrochemical cell that we have designed here. This concludes our summary and review of electrochemical cell structure and function. Hopefully this provides alleviation for any of the unanswered concerns that many students no doubt had.